So, yeah. Do you have any break between you finish school?
Yeah. August.
It'd be that guy who eats a smelly leftover burrito.
Fantastic.
Just outside. Just outside. Great. I dropped great inspection day. I was excited. Just playing around.
Just don't know if it's like we'll try again in a minute. You'll see.
I got it. I have it open. It's it failed to go live.
Yeah, there's like a little thing that popped up. We'll try again in a minute.
It says we're live right now. All right.
We're gonna listen to it or not. Let's make sure everything's live.
We're not. I've got it up on my screen. I'm just gonna go grab headphones so I can listen to it during ish.
When Darnell was getting in his car as he was driving by.
Why are you driving here? That's right.
Because they were incredibly late.
(2015) brown bag for the TRC. Today we have Matthew Brand, a recently graduated undergrad from UVM and now a graduate student at UVM at the College of Engineering and Mathematical Sciences. We'll be talking about reducing bridge count. I'd like just to point out a couple formatting items. We allow a half hour to 35 minutes depending on the presentation length for the beginning. And then we do take questions at the end, have a Q&A and discussion. And also for those who are participating online, please feel free to use the Google Chat option under the YouTube live event to submit your questions, and we'll field those at the end as well. Just a note, you do need to be logged into your YouTube account, so please do so you can submit your questions. And with that, I will turn it over to Matt.
Okay. Welcome everyone. Thanks for hearing me out. I'm Matthew Brand. Recently graduated from UVM and soon to be a graduate student. And I'm here to talk today about my work that I did last summer and throughout the year, and will continue to do through grad school, bridge tower, and using sacrificial embankments to help reduce bridge tower. So what is bridge tower? Bridge tower is defined as the erosion removal of bridge embankment or bed material from underneath or around bridge foundations. This is just a classic example of a bridge tower and what bridge tower would look like. where you can clearly see that the embankment has been, or the bridge foundations has been eroded out from underneath it. And so bridge scour comes in all sorts of different magnitudes. And these are important when determining risk of failure due to bridge scour. So this first image here shows a bridge foundation. On the left is just a typical slab footing foundation, and on the right is a driven pile foundation. And the hashed lines show the bridge stream bed during show a bridge stream bed. And so this first condition here is just what we would consider stable condition. There's no need to worry. It should be monitored, but it shouldn't. There's no remediation needed immediately. The second condition here shows what we would consider like a medium condition, scour condition, and it's just when the top of the footing is shown, or when the piles are just being shown as well. And this is not something to be immediately concerned with, but it definitely is something that you have to monitor more closely for the future, especially after large flow events. And finally, there is scour critical. And so a scour critical bridge is one where the foundation is undermined and is considered unstable and should be remediated as soon as possible. And so the Federal Highway Administration conducted a study called the Bridge Scour Evaluation Program, where they determined, where they tried to figure out how many scour critical bridges there are in the United States. So there are currently 23,000 scour critical bridges in the U.S. With over 40,000 unknown foundations. And the amount of scour critical bridges in the U.S. is about 5% of the total bridges in the United States. In Vermont, there are 305 scour critical bridges, long structure bridges that are considered scour critical, which represents about 11% of the amount of total bridges in Vermont, which is a little bit higher than the U.S. average. This is post-Irene data. And so the reason why this is a big issue is because it is the #1 reason for bridge collapse and failure in the U.S. Just most recently, Bridge I-10 linking Phoenix and Los Angeles collapsed on the interstate highway out in California, which was a huge issue and has caused significant traffic delays. And obviously, Hurricane Irene in Vermont was pretty significant and caused some major bridge damage and bridge collapse, and a lot of that was due to bridge scour. So when talking about scour, there's some significant differences that are very important, especially when we're talking about the future research that I'm going to do, which is the difference between abutment and pier scour versus channel flanking. Both fall under bridge scour. However, abutment and pier scour is the removal of bed material from underneath the bridge foundation itself and directly around it. So you can see in this image here that the bridge foundation and piles, much like that image in the manual, the piles are shown because the bridge foundation itself was eroded out from underneath it, as compared to channel flanking, which is the erosion and removal around the bridge, of material around the bridge. So the waterway actually just went and eroded the embankment that leads up to the bridge rather than underneath the bridge foundation itself. And so this analysis was done by Ian Anderson at UVM, which found that scour damage, on average, when it comes to repairing the bridge per square meter of deck area, is more expensive to repair than channel flanking damage, especially because oftentimes scour damage will can lead to bridge collapse, which is a major repair cost, as compared to channel flanking damage, where you just have to backfill in this area here and then pave it over again, re-armor it if you want to, and then the bridge is ready to be serviced once again. And so the average repair cost for scour damage in Vermont due to Tropical Storm Irene was $240,000, as compared to the average repair cost for flanking during Tropical Storm Irene, which was $70,000. And so last summer when I was working under the TRC Undergraduate Research Award, we were working on this problem of bridge scour, and we were interviewing a professor, Professor Richard M. Downer, and he was telling us about his experience as a Flume employee post-Irene, and inspecting all these bridges that had failed during Irene, and looking at their reasons, and looking at everything and assessing costs. And he noticed that bridges that had experienced channel flanking damage were often repaired much quicker and cost much less to repair as compared to bridges that had experienced bridge scour. So while this is an image of channel flanking, and while this image looks bad, in reality, repairing this is much, much easier than either replacing an entire bridge because it collapsed due to scour, or getting into the stream bed itself and trying to repair the scour and refill in areas that have eroded away due to scour itself. So while he was telling us about this, we started thinking about ways that we could create almost like a fuse where the channel, you would force a stream to do channel flanking damage as compared to bridge scour damage to help reduce costs and make a bridge more safe and easily repaired after a large storm such as Irene, instead of having experienced a large amount of bridge scour, which is much more dangerous in almost every way. So the way we wanted to think about doing this was we set up an experiment in a flume, which for those of you who aren't familiar with what a flume is, it's basically a large rectangular channel. And we have one in Bodie Hall that you send water down, and you can set up all sorts of hydraulic experiments in the flume. In a flume to simulate what a river would do. So I set up an experiment in the flume using to try and simulate this type of damage, scour damage versus channel flanking damage, and try to create almost like a fuse using a sacrificial embankment to simulate what Professor Richard Downer saw. So what I did was set up an embankment, and then I also cast a concrete abutment, which you can see right there. Cast the concrete abutment and put it inside of my embankment. And then the stream channel itself was just made out of sand. And then there's also the stream bed here, or the stream bank, which I made just with a non-erodible gravel. And so in the flume, I was able to use the laws of similitude to best try and approximate what would happen in real life and try to best simulate what would happen in the real world. So this is a elevation schematic of the experiment that I set up. The abutment itself is about 15 centimeters wide and 20 centimeters tall. And this over here on the left represents the gravel that I put there. And so that would be sort of like the armoring. If you were to heavily armor an embankment so that you wouldn't want it to erode, which is generally what happens today. You don't want embankments to erode. That simulates the heavy riprap that would not collapse or erode away during a large storm. And right here in the middle, I just put sand that would simulate a stream bed, and simulated with the flume 100-year storm. And so this is what the setup looked like in real life with all the gravel there on the left, and the stream bed right in the middle, and the abutment, the concrete abutment there. I didn't actually build a bridge deck because that would have just taken up too much time. So you kind of have to imagine a bridge deck going across the stream as well. But the abutment performs its job. And so I then ran the simulation with the flume. And so just as you would expect, I ran a 100-year storm, simulated a 100-year storm through the flume. And sure enough, the gravel embankment did not erode away. It performed just like many embankments do today. And you can see sediment being carried away. You can't actually see the scour holes developing underneath because the river is too muddy. But you can see a lot of sediment being carried away from the back here, which is a scour hole developing. And so with that, I had kind of my baseline. What would happen with a typical bridge during a typical large storm. So then I worked with proposing a design with creating this fuse. So how would we create this fuse? So my thought process was you wouldn't design the fuse to erode away during low flow events, just normal little storms where you wouldn't want the channel to, you wouldn't want the embankment to blow out before the bridge does, but only during a storm event that you would consider dangerous. So for my Flume experiment, I just arbitrarily chose a 50-year design flow, where after above a 50-year flow, the fuse would activate and the embankment would erode away past that flow. So the way I did that was I armored the embankment up to what the 50-year water level height would be, which you can see here. This is all just gravel still. And this is all armored embankment. It's not going to erode away below the 50-year storm level mark. But above that mark, I put a very highly erodible sand that would theoretically, I didn't know if it would, theoretically erode away in a very fast manner after the water level reaches that height. And so theoretically, this being the water flowing down, after it reaches this height here at this red mark, this would erode away and open up that channel to allow additional flow and also debris passage that would theoretically reduce scouring. And so this is how I set it up in the real world. With this now, as you can see, is now like that sand that I put in there instead of the gravel. And once again, everything is just the same as it was before. And so I ran the experiment, ran the large flow down, and it's a little bit difficult to see here, but if you watch the black rings on one, you can see the sand actually eroding away itself. And the whole thing eroded away in a couple minutes or so, which was great. And this shows the actual outcome of that experiment itself. The embankment completely washed out, but there still was the armoring that I wanted to stay there. So the embankment completely washed out. And so what this did was that I was able to compare the results from my fuse design for Scour as compared to the traditional design. And the results were pretty large, pretty staggering. So if you look at the traditional design, you can clearly see that the abutment has been completely undermined. And what you can actually see is that it's settled quite a bit. I actually took measurements of where the abutment was pre and post storm. It actually settled quite a large amount and twisted, which would be really, really dangerous. And this would be considered scour critical, or possibly even failed, which is, a big, big problem. Repairing this would be very, very expensive, very time consuming, as compared to the fuse design where the embankment washed out. But if you look, just the little top part of this slab footing is showing, which would be considered on that medium range of scour rating. Which in terms of repairing, you wouldn't necessarily even need to repair it past the embankment, but just monitor it closely in the future. So this was, I consider this a pretty big success. And so this is just another schematic showing how much the stream bed migrated during my experiment. So this dotted line here shows the original stream bed, and the solid line here shows the stream bed after the experiment. And this is with the traditional abutment design, highly armored embankment, doesn't erode away. And you can see that the original the stream bed migrated very, very much during the experiment, and it undermined the abutment quite severely. And this is with the fuse, and you can see it just shows the cap here, and that the abutment is still firmly embedded inside the embankment. Which was pretty significant. So with all this data, we wanted to keep the project going. I was really interested in the project. I thought it had a lot of potential to keep moving. So Professor DeWalker and the senior design team at UVM was able to set us up with actually doing a design for a real bridge, looking at a real world application for a bridge. So we looked at the Quinlan's Covered Bridge in Charlotte, Vermont. It's about 30 minutes south of here. And it crosses the Lewis Creek at the intersection of Spear Street and Moncton Road. So if you just keep going down Spear Street, you'll eventually see a covered bridge. It's really pretty. But you can see this is the river. And you can see that the river is cut off from its floodplain by Spear Street itself. So it's pretty constricted by this small bridge. This covered bridge isn't very long, so it constricts the flow at this site. and it's currently right now has a Scour critical rating from VTrans. So our team's job was to come up with a remediation program for remediating the site to remove its Scour critical rating of this bridge. And so we came up with a bunch of different designs, but the one I'm going to focus on is the fuse design itself. We first had to come up with a hydraulic analysis to get existing conditions of the site. So what we did is we created a HEC-RAS model using cross-sectional data from South Mountain Research and Consulting Group. They generously provided us with data that they had collected in 2000, about 4 years ago. And so we were able to come up with an existing condition for the site using that cross-section data, but also StreamStats, which is a USGS program that estimates flows based on regression equations. And so we were able to get different design storms and set up our model. And so with this model, we were able to calculate scour depth using HEC-RAS, which is the Hydrologic Engineering Center's river analysis system. It's the traditional method that agencies and different companies use to simulate and model rivers and come up with scour estimates. And so here's a three-dimensional image of the river itself after we ran a 100-year storm through it. And so you can see that the river is quite flooded and that this embankment is completely cutting off the river from its floodplain during a large storm event, which constricts the flow and forces all the flow to go directly underneath the bridge, which increases the velocity and then increases the scour pretty severely. So what we did to simulate a fuse was we just removed that embankment during a storm to simulate what a fuse would do, saying the fuse will erode away and the embankment will be gone. But now this river has access to its entire floodplain during a large storm event and would theoretically reduce the flow velocities quite substantially. And so we were able to use HEC-RAS's in-house scour calculator. And so for the traditional approach of building, we found calculated scour depth of 35 feet, which is very, very large. And that we weren't able, we did our best to try and calibrate it best, but it's just, HEC-RAS has some pretty well-known issues with overestimating scour. So we decided to focus more on the relative drop in scour based on our design rather than the absolute numbers. And then so with the fuse system, we were able to calculate a scour depth. We calculated a scour depth of 25 feet, representing a 10-foot drop in overall scour depth, which is huge, which also really nicely correlates with our physical model as well. Our physical model wasn't of this bridge, but it was nice to see that both the computational and the physical models relatively, matched up more or less. And so with this, we also performed a cost analysis of the fuse system and found that the fuse system was by far and away, or not by far and away, but the cheapest option out of all of the options that we had looked at. And in addition, I actually was going through old senior design papers as well while we were doing this project, and actually found an old senior design project that had looked at another covered bridge that was consistently, the embankment was washing out during large flow events, but they also performed like a do nothing option, which was basically the same thing as the fuse, right? The embankment washes out, but you don't armor the approach or anything like that. And they also found that the do nothing approach of letting the embankment wash out was the cheapest option for that bridge, which was really cool. Because I hadn't thought of it that way, but in reality, that's what it actually was, which was really interesting. And I'm sure that there's more cases of this. We just have to look for it a little bit more. So in terms of what the future holds for this research, I'm going to be a graduate student here at the University of Vermont, working with Ian, Professor Rizzo, and Professor DeWalker, looking further in depth into designing these embankments to fail before for reducing scour. And we don't quite know where we're going with it yet. But luckily we were funded by the National Science Foundation to keep doing this work. I was funded for 3 more years to keep doing this work for both my master's and a doctoral degree as well. And so I just wanted to thank the TRC for funding this research originally. It was really, really awesome to be able to work a whole summer with professors I love and get paid for it, which ultimately led to the National Science Foundation funding me a lot more money and the school a lot more money to keep doing this research. But also to Ian Anderson as well. He did a lot, helped me out with a lot of this work and did a lot of the analysis and did a lot of other things. And to John Lenz too, for those of you who don't know him, he's really, really helpful, really, really supportive and smart, and has just a lot of practical experience. And also Professor DeWalker and Rizzo for helping me throughout this whole thing and helping me write both my grants and Dr. Houston as well. So that's it. And thank you very much.
Now we'll just open it up for question and answer.
Yeah.
The design for the erodible bank, is that, did you try it with like a simulated material that they, like I imagine there's probably some sort of standard substrate they have to put under pavement or whatever.
Yeah.
Is that in the plans for probably the larger scale effort, or did you try to simulate that in the tank as well?
Yeah, so simulating that tank wasn't really possible.
Yeah.
Just because, especially when you're doing similitude studies, for Scour, it's very, very difficult to do that because once you start scaling things down too much, you actually start getting like, if you're trying to simulate like gravel, cobble, boulders, and sand, if you try to scale that down to a flume study too much, you actually start getting into clays, which have cohesive elements to it as well, which messes you up entirely. So for the flume study, no, I was not able to do that, unfortunately. But in terms of our future work, that's definitely something we have to look at. We have to consider roadway design and will a road support a traffic load? Will the fuse support traditional traffic loads if you're putting like a sand instead of like a big gravel that you normally would for a road? So that's something we definitely have to keep looking at and keep doing future research on.
I haven't thought about it with a question. So remember, Krell has flumes that would be much more appropriate than the one that we have in hydraulics on, because I know the problems we ran into.
Yeah.
We were like, well, that's one of the reasons we had a 50-year storm, right? We just have the flow rates in that flume, given this particle size that you have to get it down to.
Yeah.
To do great scaling. But Krell has some really big, amazing flows. We should at some point go over and look at what they got, because I know they're interested in collaborating with people on research. So we really want to get cold regions.
Oh yeah, we actually were.
Lab, right?
New Hampshire?
They're right in
Right over the border.
Yeah.
Context there, so.
Yeah. That would be great.
And then another question I had is, so the erosion's really good for saving the bridge.
Yeah.
But it seems like it could also open up some safety concerns if the road collapses. I mean, like, so for obviously certain bridges, they're only going to face the 100-year, flood every 100 plus years.
Mm-hmm.
But in regions where this might actually be most critical, could be places that flood more frequently. An example would be, the buried Plainfield area right now, which has been suffering from floods, it seems like every 3 to 4 years. So would you also kind of have to come up with some sort of like warning and maybe some additional safety features that might need to be integrated so that people, it may not look like the erosion's taking place on the road surface, but obviously now you've got pavement just kind of hanging out in the breeze there.
Yeah.
Is that a consideration that you had made, or?
Yeah, well, we were talking to V-Trans actually. They were pretty concerned about that because pavement can kind of support itself. Yeah. It's pretty strong. And if someone drives over and collapses, then that's a big issue. So yeah, once again, that's just something we're gonna have to look into. Luckily the grant goes on for 3 years, so I have a lot of time to keep researching this sort of thing. But that's definitely something on the list that we have to look into in terms of, and just thinking about how do we make sure that safety is considered as well, and then also making sure that, like if you're letting part of the bridge go away during a big storm, it could cut off communities as well. If that's the only bridge leading into town, you certainly wouldn't want to implement this to do that for that sort of purpose as well.
This will be more for, I guess, for old bridges that are already around that you cannot really fix for current standards. For the new ones, you could make them longer and those kinds of things. So Perhaps if you are expecting another tropical storm ID, you can just close down the bridge for during the storm, you know.
Which I think they're doing in some communities anyway, so yeah, maybe it's not point.
The other thing is, I don't know where you want to take it, I know our business to come up with ideas, but I remember the senior design project that did the, I mean, I helped to do the do nothing calculation, and one of the ideas was that if you wanted to consider a little bit more of the geomorphology up and downstream of the bridge.
Yeah.
There was a location, I remember, that had a huge agricultural field, and one of the ideas is you could put the fuse in much further up or much further down, so that it didn't have to go around the sides of the bridge. So if you, I don't know how far you want to extend it, but you know,
Yeah.
Jordan, I know, is interested in the geomorphology side of things, but it does require doing a more in-depth modeling that includes large portions of the channel.
Yeah.
And it still has to be done on a site-by-site basis.
Yeah.
So you have to have the right conditions to allow a fuse to
Yeah.
occur
Yeah.
earlier or later.
We actually just basically created a recent case study. We had our UAV project and we flew over the Plainfield, Great Brook area. And that's exactly what happened was the bridge actually held up really well. The road held up okay, but because they had reinforced it so much, it went up and over the banks and expanded. You could see where it had gone, I mean, around, like, I mean, it was 50 plus feet in either direction, where maybe there had been some sort of built-in either additional channel or some other way that they could have, because the bridge, they can't make it any wider. It's permanent. It's been like that for like 80 plus years now, so it's there for keeps. But that would definitely been a solution.
If I'm not mistaken, it's a bridge that could be shut down for a couple of days without significantly affecting it.
It is right now. Yeah, there's other ways
It's
around it.
not usable and they're doing it all right, so it probably would have saved
But we've got some cool
thousands
data.
of property.
They want to
let
take
the
a
bridge
bridge
go. So.
Yeah. Oh,
Is
yeah.
that effectively what the relief culvert option does? To divert water out another way, because that was the second spot. Sounds.
Yeah. It was like putting, Jordan worked at the project.
Yeah, it was just implementing a concrete box culvert that kind of just went under the approach to the bridge. So as the flows got high enough, you know, a certain portion of the water went underneath. So not everything was going right under the bridge, so lowering the velocity was kind of potential.
But if you looked here, we would have put it right about there, just because look at the place itself, you see that the river is kind of wants to go this way, right? There's a natural floodplain here, and the river keeps on going this way. So this is the abutment that's having just a lot of issues because the water is just slamming right into it, which is a big issue. And actually, the data that the one Kristen Underwood is the person from South End Research and Consulting, and she was telling Jordan that the town kept on paving over the road instead of ripping up the pavement and then repaving it. They just paved over and over and over. So there's like 4 layers of pavement below that. And her suggestion to the town was actually to rip up all the pavement, pave it back over again. But if you lower the elevation of the road itself and you let the road be overtopped at that area, during a big storm event, that would relieve a lot of the pressure and be a really cheap option. But the town had, I believe it was, she said the town had a lot of issues with letting the road get overtopped during big storm events. They didn't want that to happen, where the road wouldn't be usable during like a large storm. But right now, this is a very, very heavily armored.
Well, some of the education you save yourself on the bridge, you got sound later on.
Yeah.
Mother Nature backs off.
Yeah.
Can you bring back up the schematic of this for the, I think it's like the next, yeah. So, and then I was just having a little bit of trouble orienting myself. So
yeah,
it's a hard image to catch.
So where is Spear Street?
So Spear Street is right. It's overtopped right now.
Okay.
So this is Moncton Road. This is the embankment that Moncton Road is protected by. But Spear Street is right along here, and it's protected by a berm. But during the 100-year flow, it's actually overtopped.
Yeah.
According to the model that we created. So Spear Street is overtopped, which makes it a little bit difficult to see in this case.
Okay.
Yeah, thank you. And another actually solution that was proposed for this, we had the whole report, which was really helpful, was actually lowering the, there was a berm protecting Spear Street from overtopping events. And one of the solutions proposed is actually removing that berm and lowering it so that once again, Spear Street can be overtopped. Because this whole bridge, you can imagine, is you're taking all of this flow from here and just constricting it down to one little area, which is just really, it's a tough place for the bridge to be. It's kind of like they chose the smallest possible span they could, because it's a covered bridge. You know, they can't really make it that long. Whereas nowadays, you know, we try and make bridges as long as we can to allow for as much passage of water through, especially in the floodplain areas. But once again, this is more for the idea of the Fuse is that it's a retrofit for bridges rather than a design. So you wouldn't design necessarily a new bridge with this. It's more, you have a covered bridge that's been there for 150 years. How do we make sure that it stays there for another 150 years?
You can only do so many remediation techniques to a historic bridge.
And for this project, getting rid of the bridge was not an option.
Yeah, replacing the bridge was not gonna happen. That was not even considered. Just
Well,
because.
it's the same, yeah, the historic bridges, just, and it only has like 3 people across it, I'm exaggerating, but they're not gonna let you get rid of those beautiful covered
Yeah.
historic bridges, you know?
No, means one option is to relocate it somewhere and create a different bridge here, you know, the state has done that, they have historical bridges for this place. But they don't want to do it here.
I could also see this thing's already
I believe so.
There are a lot of covered bridges around the state sitting in V-Trans garages.
Wait, possibly.
Yes, I can see this also benefiting private bridges, because I know that during Irene, there was a lot of private bridges that were destroyed, and there's just no means to replace those, where I'm sure that people could care less if their driveways or, you know, the road leading up to it got destroyed.
Yeah,
That's much easier.
yeah.
From
Yes.
a stream ecology perspective, when you did your modeling, was the net amount of displaced sediment different between the two scenarios? I mean, you're putting up a big bunch of stuff and saying, we're gonna send this out to a road, so all of a sudden you're introducing more material into the stream.
Yeah.
But you're having less erosion in the bank, so I don't know if you measured that trade-off or not.
Yeah, no, we actually didn't, but that's a really interesting point. Jordan actually brought that up during our design, when we were senior design. But yeah, you don't really know what the trade-off is until you actually do the calculations yourself. And for the scale and scope of our senior design project, we weren't able, we were pretty pressed for time.
Sure.
Yeah.
So we could estimate pretty good how much the Fuse is gonna release the sediment, because we're putting in non-erodible material where the actual depth of the scour that's going would be a little harder to measure, but I would imagine the Fuse system would let off more sediment than what is actually being taken away from it.
But it's also directly in the floodplain, so that's where you want the sediment to go, as where with the scour, it's increasing speeds in the channel and causing bed degradation, not just at the bridge, but in the channel overall, which is going to cause more bank erosion because you're changing channels. Sort of there's 2 ways to protect the bridge. One is to harden and armor more of it, and the other one is to deal with the stream. And in this case, the stream wants to continue to migrate to the right, but as you can see, they've built a large wall.
Yeah. So, I mean, the water, you can see it, even during low flow scenarios, was just hammering away at this wall. And they, you know, the wall is pretty recent, and they have been just armoring it with just huge riprap constantly. And the bridge actually itself is kind of interesting. It's a little bit off topic, but this is all new. This is all new. Everything basically is new except for a few beams in the side of it. They just,
And it has steel I-beams that are it's reinforced for snowplows and school buses.
There's a few, a few really old pieces of
they're very pretty, actually. They're very cool. But yeah, no,
So school bus actually goes through it.
yeah. And heating fuel trucks. That was another big consideration, was that you know, emergency vehicles and stuff have to be able to cross this. and fuel trucks too is huge.
Another probably question you're not going to answer for, but just off the kind of what John said is, are you going to maybe plan for debris and stuff? And that's one of the biggest concerns. I mean, that's kind of why we're flying a lot of these brooks and stuff, is because there's entire trees, just piles and piles of them. And maybe see how that may affect it, because obviously if the flow rate is spread out over a much greater area, it's probably not going to carry as much debris downstream, which might be beneficial to the bridge as well. Because obviously that's what destroys a lot of bridges, is actually the debris just piles up and starts pounding away at the bridge structure as well. So but I'd be kind of curious to see what the impact would be on that as well.
And that might tie more to what sort of, Donna had mentioned about having a few substrate.
Yeah.
If you reduce the flow rates further up, then that's sort of solves that problem. So.
Yeah, once again, something we have like actually like investigated, but like we've theorized that yes, we would imagine that debris would be able to go around the bridge as well. And you're right, debris is a big issue because as it starts piling up, it could further constrict the flow even more. They're increasing the scour, and it's just one of those compounding things that really messes up on the bridges and can cause superstructure damage as well. But yeah, that's definitely something that is another question that we definitely should investigate if we can, if we have the time for it. But, yeah.
One thing that I think would be also worth considering over this next 3-year period is the stationarity of the idea of the 100-year storm.
Yeah.
Meanwhile, 150-year storm, maybe that's a 100-year storm.
Yeah.
And the place that I think that would be particularly important is probably those cost projections, because that assumes some rate of incidence, and if it's wrong, maybe your cheaper one becomes yet more cheaper.
That's another big thing too, is that this is while you certainly can't implement this in every bridge. One, it helps, we notice in our HECRES model, help reduce velocities all up and downstream by a pretty significant amount. But also too that this allows for, theoretically, the higher the water goes, the more area you're getting. You can see it. You're getting all this extra area, but the higher the water goes, you're still getting more area. It's not like, it's like a culvert, which is you hit a certain.
Kind of the ultimate downstream, like maybe the most important bridge or something.
Yeah, definitely. Like the private bridges that maybe constrict flow really far upstream and cause issues. It might be a good idea to install a bunch of fuses in those, and then that way it helps save downstream bridges that are more important to you. And also just looking at how it affects the river system as a whole. Instead of just one. We looked at one bridge, because that's all we really had planned for. But I think it'd be really interesting to look at a whole river system and installing them strategically in areas that wouldn't be too detrimental to the transportation impact, but would be really, really helpful for the stream health if you were to open the stream up.
Which ties into John's comment, because same 100-year storm, right? Isn't a 100-year storm in every location in the channel. That's the bottom of the range. Some of the locations were 500-year storm, but it was site specific.
Yeah, and that bridge in California too, it's just amazing. They got 5 inches of rain, and normally it's a completely dry stream bed, but they get 5 inches of rain upstream, and it's just completely washed out.
It was mostly the abutment flanking type. Is that correct from the picture? It looks like
in looking at one of the videos, it looks as though the bottom of the abutments, which were set really wide from what the center of the channel would be, the bottom of the abutments were 4 to 5 feet above the bottom of the stream bed, and then they had 15 feet of armoring embankment inside the abutments, and that all just went away.
and it wasn't on piles. It was
No,
just
it
shallow
wasn't.
foundation, which we can do for it.
abutments, they had piers, so they thought that their abutments were wide enough back outside of the channel. It's in the desert, so the sand's pretty erodible.
Thank you.